Hello, and welcome to my Physics 2212 Lab 1 report. The purpose of this lab is to observe the interactions between charged pieces of clear tape in order to determine how much excess charge is on one piece. I modeled this via experiment and glow script. For the experiment, I used clear tape, a ruler, scissors, the table, and boxes as support. In glow script, I modeled the tape first as a point charge and second as a line of charges. The fundamental physics principles are the idea of charge, including Coulomb's law, which states electric force equals 1 over 4 pi epsilon naught times Q1 Q2 over r squared times r hat. Newton's second law, which says force equals mass times acceleration, electric force, which equals charge times the external electric field, which equals 1 over 4 pi epsilon naught times q over r squared times r hat, and then 1 over 4 pi epsilon naught equals 9 times 10 to the 9th Newton meter squared per coulomb squared, and the charge of a proton is E equals 1.6 times 10 to the negative 19th coulombs. To make the charge tape, I placed a 15 centimeter long piece of tape on top of another piece of tape, then ripped it off. As you can see, the top tape became charged and is attracted to my hand. I expected two pieces of tape to be attracted to each other, and my observations confirmed that, as evidenced in this first picture. The tape was also observed to be attracted to neutral objects, in this case my calculator and a pair of scissors. To find out if the tape is positively or negatively charged, I tested it with a negatively charged plastic pen. If the tape is positively charged, it should attract to the pen. If negative, it should repel, and if neutral, it should also attract. I observed that the tape was attracted to the pen, meaning the tape must be positively charged. I suspended a charged piece of tape between two boxes, tape B, which is the system, and brought another charged piece of tape below it, tape A, which is part of the surroundings. Since the momentum of tape B is not changing, the net y component of the force on tape B is comprised of gravity and the electric attraction to tape A, which cancel out to zero. Tape A exerts a mainly vertical force on the floating portion of tape B. To determine the gravitational force on tape B, I need the mass of the tape. Knowing that the tape is 1 gram per meter, and I used 15 centimeters of tape, means that the mass is 1.5 times 10 to the negative 4th kilograms. I can assume that the tapes have the same net charge because they are the same material and length and undergo the same process. I am also assuming I can model the tape as a point charge. In my free body diagram, you can see that the electric force is acting in the positive y direction, and the gravitational force is acting in the negative y direction. Force equals mass times acceleration, and the acceleration here is only due to gravity, so 1.5 times 10 to the negative 4th kilograms times 9.8 meters per second squared equals 1.47 times 10 to the negative 3rd newtons. The separation distance was approximately 4 centimeters, or 0.04 meters. Because the tape is motionless, we know the sum of forces must equal 0, so we can say the magnitude of the electric force equals that of the gravitational. Rearranging and plugging numbers in results in the charge being 1.62 times 10 to the negative 8 coulombs. The length of the tape was 15 centimeters, or 0.15 meters, and the width was 3/4 inches, or 0.01905 meters. The number of atoms is the area of the tape divided by the area of an atom. The area of the tape is 0.0029 meters squared, and the area of an atom is 1 times 10 to the negative 20th meter squared, so the number of atoms is 2.86 times 10 to the 17th. The electron loss fraction is the tape charge over the electron charge, which is 1.01 times 10 to the 11th. The ratio of electrons to atoms is thus 3.54 times 10 to the negative 7th, meaning there is a deficit of electrons. Now for the computational glow script model. I modeled both tapes as a point charge. The second part is the gravitational force vector. The next part is a function to calculate the electric field from different observation locations. This shows that the magnitudes of the electrical and gravitational forces must be the same. Here's a rearranged equation to find the charge. Next is the electron amount and ratio of electrons to atoms. Here's the output where you can see the orange arrow is the electrical force and the green arrow is the gravitational force. Now for the line charge model. Here are the constants. Note that I estimated a different Q than what I found earlier for a point charge. Here's the same function that calculates the electric field from different observation locations. Here's the function that creates the line of charge, which was given to us. This is creating the tapes as line charges. Then we calculate the electric field and electric force. Scaled to see easier. This next part is a function to find the electric field at the top tape and create its arrows. This is creating the gravitational and electrical force arrows. This is the output. The green arrows are the electric field, the white arrow is the electric force, and the yellow arrow is the gravitational force. The magnitudes of the electrical and gravitational forces are very similar, as expected, would not be if I had used the charge I got from the point charge calculation. To summarize the experiment, the tape length was 0.15 meters, the tape mass was 1.5 times 10 to the 4th kilograms, the distance between the tapes was 0.04 meters, and the magnitudes of gravitational and electric forces was 1.47 times 10 to the negative 3rd newtons. To summarize the coding, the magnitude of charge modeled as a single point charge was 1.62 times 10 to the negative 8th coulombs. The magnitude of charge modeled as a line of charges was 2.6 times 10 to the negative 8th coulombs. The assumptions, approximations, and idealizations were that each piece of tape has the same amount of charge, we can consider the tape first as a point charge, then as a line of charges, and we can neglect air resistance and friction. What if electrons were positive and protons were negative? Nothing would change because those labels are just words. They would still be opposite of each other and attract to each other. For example, the negatively charged plastic pen would now be positively charged, and the tape would be negatively charged, but the tape would still be attracted to the pen. Specifically, the magnitude also would not change. Why do different models result in different charges? The electric field of the line of charges is lower than that of a point because the ends of the tape are farther away from the observation point. Because of this, the charge of the line must be higher to equal the same amount of force from gravity.